Thank you for the invitation. So today we'll talk about a very basic and fundamental network problem, that of broadcasting a piece of information in a network. So we assume we have a connected graph G on n vertices, and initially some arbitrary node knows a piece of information, which we call the rumor, and this rumor must be disseminated to all the other nodes in the network. So randomized rumor spreading is a very basic algorithm for solving this broadcast problem. For most of the talk, I will talk about the synchronized version of these rumor spreading algorithms, where nodes take steps in synchronous rounds. Towards the end of the talk, I will talk about also asynchronous versions of randomized rumor spreading. But for now, I will assume round-based protocol. So in the push version of this protocol, in each round, every informed node, every node that learned the rumor in some previous rounds, select a neighbor uniformly at random and just sends, or as we say, pushes the rumor to that node. So the pool rumor spreading algorithm is symmetric. In each round, every node that has not learned the rumor yet just selects a random neighbor, and if that neighbor knows the rumor, then it sends the rumor to the uninformed node, in which case we say that the rumor is pooled. And yes?
Pushes doesn't mean that you will not send it in the other round again?
No. Rounds are independent. No, so push.
If the node is informed, they will do the same thing.
Yes. And finally, the push-pull algorithm is a combination of both strategies. Every node selects a neighbor to either send the rumor to that neighbor if it already knows the rumor, or to request a rumor from that neighbor otherwise. Okay? And here is a simple example of an execution of the last of the push-pull protocol. Initially, we assume that this red node knows the rumor. Yes? Yes. So, how do you know if you are uninformed?
Yeah, but you send to somebody who already knows.
Let me tell you this example, and if you don't understand. So this is an example of the push-pull protocol. So this red node who knows the rumor chooses a random neighbor to push the rumor to inform that neighbor. So let's say this red arrow indicates which neighbor it chooses, and every blue node, which is a node who does not know the rumor yet, choose a random neighbor and try to pull the rumor from. For example, this arrow says that this node will try to pull the rumor from that random neighbor, of course unsuccessfully because this node does not know the rumor. So after the first round, only one node gets informed. In the next round, yes? It's not
pulling from the first
push.
No, it's pulling from the other. That is a
I'm saying not pulling from this. But it's still receiving the one from the pushing. So the pushing is not. It's not that a rumor can only go when one pushes and the other pulls.
No. In fact, yes. In fact, each node, as you will see in the next round. So this is after the first round. The second round again, just one node gets informed because of push. Then we have two successful pulls in the next round. So these two nodes get informed. And then in this round, it happens that these two nodes choose to push the rumor to the same node, and that node gets informed. So, yes?
At the beginning, each node knows only its neighbors, right? Or they know the graph?
This is the graph. Sorry, the nodes, they just know their neighbors. But this is irrelevant because now I'm just describing the protocol. But for the protocol, they just require to know the set of their neighbors. Okay? And the main question we will be interested in is how long it takes before in a given graph or all nodes know the rumor. Okay? So is it the protocol clear?
So
Yes?
actually, so it means that things would be spreading even with only having a push protocol or only having a pull protocol, right?
Yes, of course. This is just one of the three versions that I described, yes. But I will mainly talk about this push-pull protocol. Okay? Why to study such a protocol? It's a nice, simple protocol, requires only one local decision in each round. The nodes do not require to maintain any state other than the rumor. Each node needs to send, to initiate only one connection to another node. Of course, it may be called by more than one nodes, but by more than one other neighbors. But in any case, this requires this results in a protocol that is in general message efficient. Also, due to its randomized nature, it tends to be robust to various types of link and node failures. I will not talk about these issues in detail. And finally, we will see that despite its simplicity, it's fairly fast for many graph topologies. And for example, compared to other standard solutions for broadcasting information, it tends to require fewer messages than flooding algorithms. In the flooding algorithm, a node, once it gets informed, in the next round, it sends the rumor to all its neighbors. And also structured deterministic broadcast algorithms, it tend to be more complicated. They require knowledge of G, and they are more sensitive to failures. Okay. And it has found several applications. In fact, it was initially proposed as a way to solve the distributed maintenance problem of replicate databases. And it has also found applications to data aggregation, resource recovery, failure detections, and others. Moreover, it has been suggested as a very simple model to explain why information in fact spreads quickly in social networks. And I will talk about this more a bit later. Also, various performance measures of these algorithms have been studied in addition to the running time. By running time, I will mean the time until all nodes get informed, all nodes learn the rumor. So in addition to this parameter, several papers have studied questions related to the number of messages, robustness to failures, and the amount of randomness needed by the protocol and how to reduce that. But I will focus only on this first parameter. And so several papers have shown very careful bounds, very precise bounds on the running time of the push protocol for various graphs. For example, the complete graph, hypercube, random graphs, or random regular graphs. In all these graphs, rumor spreading requires only a logarithmic number of rounds to spread the rumor, which is very fast. So moreover, for general graph, it is known that n log n rounds suffice to spread a rumor. Okay, this holds for any. This is an upper bound that holds for any graph, connected graph. Yes.
Is the runtime the expected?
Yeah, it doesn't make much difference. You can think most of the time I will talk about the time until all nodes get informed with high probability from the worst case source node. Okay? But in most cases, expectation and with high probability results are the same within some factors. Yes? Yes?
Does this result hold also for expanders or only for?
Which result? These are for these specific graphs, and this last result holds for any connected n-node graph.
But the results for random graphs also holds for expanders or no?
Yeah, I will talk, yes, in expanders it also takes log n, but I will talk about this in more detail a bit later. Okay, so for the push-pull protocol was initially introduced in order to reduce the number of messages essentially for rumor spreading the complete graph. But subsequently it was observed that it performs significantly better than just pull or push in several interesting families of graphs where you have a wide variation between node degrees. And in particular, it was shown that it requires that is very fast in these preferential attachment graphs with a certain range of in the preferential attachment graph and also in this other type of graphs. Both of them are used as models for social networks. And so this completes my introduction. So this is the structure of the remaining of the talk. So in the previous slide, I presented some results for specific graph topologies. There is also some work that has shown general bounds on graphs, on the rumor spreading time on graphs that hold in terms of expansion parameter of the graph. So I will talk about this in the first part of the talk. Then I will describe some works that on more sophisticated dissemination algorithms that use these results that I will describe right next, these bounds in terms, or rumor spreading in terms of the expansion. Then I will talk a little about rumor spreading on graphs that change over time. And finally, we'll talk about rumor spreading on a synchronous time model. Okay? So bounds with expansion. Two standard expansion parameters have been studied with in relation to the rumor spreading time. I will just briefly review the definition here. The first is the conductance. So the conductance of a graph G. To define that, first we define the conductance of a set S of vertices. The conductance S of this set is the ratio of the number of edges leaving that set over the sum of the degrees of the nodes in set S. Okay, so the edges leaving the set over the sum of the degrees is called the volume of the set. Okay, this is the conductance of the set S. The conductance of the graph is the minimum of the phi of S over all sets S that have volume at most half of the total volume of the graph. Okay. The second measure of expansion, it's called vertex expansion, is also standard. Again, we define first the vertex expansion alpha of set S. Now it is the number of neighbors of this set 4 over the cardinality of set S. So 1 in this case. And as before, the vertex expansion is the minimum over all alpha of S for all sets containing at most half of the nodes. So here, you see here we have the cardinality of S, here we have the volume of the S. So this is the difference. And very, very quickly, so both parameters takes value between 0 and 1. 0 means the graph is disconnected. Values closer to 1 mean typically better connected graphs. Okay? For example, an example of a well-connected graph is the click. Both parameters have value close to 1. A graph that is not well connected is the cycle. Both expansion parameters have value close to 1 over n. Okay? So despite the fact that in these two examples both parameters have similar values, this is not the case in general. So there are graphs like the star where the conductance is very high. Here is 1, and the vertex expansion is low. And there are also examples where the opposite is true. So in general, these two quantities, conductance and vertex expansion of a graph, they are incomparable. Okay, and yeah, for this you just need to recall that higher values means better expansion, better connected graphs. So here is the the bounds that have been shown in terms of the first of the two measures, the conductance. So there has been a sequence of works producing tighter and tighter bounds. So in the last bound we showed that for any graph, the push-pull rumor spreading time is bounded by at least log n over the conductance of the graph. Okay, and so this means that if the conductance is constant, then just a logarithmic number of rounds suffice to spread the rumor. Okay, and this bound is tight, as there are graphs that have that diameter. For the case of regular graphs, to obtain this bound, it suffices to use the weaker push-only or pull-only protocols. But note that this is not true for general graphs. So, and here is a counterexample why push-pull, they don't always spread the rumor in time log n over phi. So remember, we said that this graph, the star, has a perfect conductance, 1. But let's see how many rounds does push need to spread the rumor. Let's say the rumor starts from the center or whenever the rumor starts. The node in the center will need to push the rumor to all the leaves of the star. Okay, there's no other way that the leaves get informed. So it means that we need at least n or n minus 1 round. In fact, we need n log n rounds, both in expectation and with high probability. Okay, so here are the bounds in terms of conductance. We also have similar type of bounds in terms of vertex expansion. This is the yes.
I didn't say it for pull, right?
Sorry.
Your last example was only for push.
Yeah, for pull. Okay, for pull, if we start from the center, then 1 round suffices. If the rumor starts from a leaf, it will take in expectation n rounds before the center pulls the rumor from the leaf. I was trying to save time. So there are similar bounds in terms of vertex expansion. We have this extra factor of log n essentially in the worst case compared to this bound here. It turns out that this extra factor is necessary, or at least something is necessary there. So there is some graphs for which this bound is matched. And as before, for regular graphs, this bound is met by just push only or pull only. Okay. Now I will give some brief ideas about these two bounds. Yes?
The regularity of the graphs is only used for the push and pull.
Sorry, again?
The regularity of the graphs is only used for in this last case or also in the first cases? Can you prove it if the graph has good vertex expansion and is regular?
And is?
And in the push-pull case,
yes?
do you assume that the graph is regular or not?
No, it's arbitrary.
Okay, and can you prove it using this kind of property?
Sorry, to prove what?
To improve the bounds, or just
This is the bound that holds for all graphs for the push-pull protocol, and it's the best possible if you only know alpha, n, and delta. If you know more about the graph, you may be able to get a better bound than this. Okay. And okay. So first I will give there's a nice simple intuition about this result with conductance. I will talk about it first. So this is our graph. These red nodes are the nodes that have been informed in the first T rounds. Okay. The key idea for the proof is to study how the volume of this set of red nodes evolves over time. Okay. So for this intuition, let's just see what is the expected increase of this volume in just a single round. And for the intuition, I will assume that I just have pulls, so I will not assume that I have push at all. And I will also assume that the volume is not too large. It's at most half of the total volume. So let's see how we compute the expected increase of the more volume. So I'll just need to consider these nodes here in the boundary. And for each node, I account for the expected contribution of that node in the increase of the volume of the red nodes in round t plus 1. So in order for node U to get informed in the round, it must pull the rumor from, it must choose one of these two red neighbors. So the probability that it happens is 2 over the degree of the node. And if this happens, then the increase in the volume of the red nodes because of this node is equal to the volume of U, which is the degree of the U. So in order to compute the expected increase of the volume of red nodes, we just sum this quantity that I just described over all these nodes. So this is the probability, and this is the volume. So this and this goes away, and what we are left with is just, so this sum is just the number of edges crossing the cut. Okay, this is it. But then remember the definition of the conductance of this set is just the number of nodes crossing over the volume of this set. So this is equal to conductance of the set times the volume. And because of this condition, we have that the conductance of the set is lower bounded by the conductance of the whole graph. And we have this final inequality. So what this says is, if we bring this to the other side, what it says is that the volume of IT increases by a rate of at least 1 plus phi in expectation in one round. And this is exactly the right rate we need to show this bound here. Why? Because if the volume increases exactly as in expectation, then the number of rounds before the volume increases above half the total volume of the graph at this rate would be 1 over phi, the logarithm of this quantity here. Remember this, the volume of the graph, the sum of all nodes in the graph is at most n squared. So this quantity is of this order, log n over phi. And so this is the number of, the intuition says that this is the number of rounds until we reach half of the volume. A similar kind of intuitive argument holds for going from volume half to the rest of the graph, considering, but now we consider the volume of the uninformed nodes, the blue nodes, which shrinks instead of. Okay, so, but this is just the intuition, but the actual proof is not much different. The problem is that this assumption here, that the volume of this set is not always close to expectation, in particular is not close at the beginning. So we need some extra ideas. And one way why you could see that this is not a complete proof is this assumption here. We only used pools, right? But we said before that we do need push-pull. Okay, so this is just all the intuition. And about the other result in terms of vertex expansion, there is no such a simple intuition, but there is some very simple technique who has been very useful so far in proving some things, and I will describe this technique to you now. So, and I will demonstrate this technique in terms of a very simple example. Okay, so this is the example that I will show. So far we assume that we have one node that knows the rumor initially. Now suppose we have more than one. We have a set S of nodes that know the rumor initially, and we have that the set is a dominating, we assume that it's a dominating set. Dominating set means that each node either belongs to the set or has a neighbor in this set. Okay, so this is a dominating set. So if rumor starts from a dominating set, then a logarithmic number of rounds of the pool protocol suffices to inform all the other nodes in the network with high probability. Okay. You may think that this result is trivial, right? Each node has an informed neighbor. It can pull from that node. But this is not the case because a node may have many neighbors, and only one or few of them may be informed. So it may be very unlikely that in a logarithmic number of rounds will happen to choose one of these neighbors to pull the rumor from. So, and note that this result does not make any assumption about expansion, although it's used for this result. Okay, one may argue that it's interesting on itself, but for this talk we're only interested in the proof. And here is the proof. So here is our graph. I made it a little larger. These red nodes are the set of the set S, which is a dominating set. And what we must show is that the rumor spreads from some of these red nodes to any given node, any given blue node U, with high probability within a logarithmic number of rounds of the pool protocol. Okay? The first step to prove this is I change the problem. I use a standard technique. So there is a standard symmetry argument between push and pull protocols, and by applying this, I will not say why, it turns out that it suffices to solve the following problem, the following equivalent problem, that if we have a rumor that starts from U now, so we have this green rumor, then this rumor spreads to at least one of these red nodes in a logarithmic number of push rounds, okay, rather than pull. So now we assume that the rumor starts from here. We assume that I use push protocol instead of pull, and my goal is to reach one of these red nodes. And I will show that this happens in a logarithmic number of rounds with high probability. Okay? So it's very short, don't worry. So let's say ITU denotes the number of nodes that have received this green rumor within the first T rounds of push. So let's say that it's like that after T rounds. And now the key idea in the argument. Look at the first round T such that the expected increase in this number of green nodes in the next round is less by a small constant factor epsilon. Okay? We proved two facts about this time t. The first is that t is at most logarithmic in n. It's not difficult to convince yourself that this is true, because I mean, if we increase by a constant factor the green nodes in each round, then it takes only logarithmic rounds before we reach the whole graph. This is slightly different because we talk about expectation, but the essence is the same. So this is the first result. The first fact we need is also very simple. So what does this say? In order for this condition to be true, it must be the case that for most of the nodes, most of their neighbors are already green. Okay? If it's not the case, so is this clear? In order for this set not to increase by too much in a round, it means that most of the push they go to already informed nodes. And in order for this to be true, it must be the case that for most of the nodes, most of their neighbors or many of their neighbors are already informed. But because of this, we should be able to show some kind of upper bound on the degree of the nodes in terms of the size of the graph. Because, for example, if all nodes had a degree, in terms of the size of the nodes already informed. Why is the case? Because if this size were very small, then it couldn't be possible, and the nodes had much larger degree than the size of already informed node. What I told you before, it wouldn't be possible. Okay. So the second fact we show is, in fact, that the harmonic mean of the degrees of these green nodes is upper bounded by the size, some linear function of the size of the number of the green nodes. Okay, and from this, this inequality here follows, which we will use in the next and last argument. So this says that the sum of the inverse degrees of all green nodes essentially is lower bounded by some constant. Okay, so how we use that? Recall that each node, so each green node, has at least one red neighbor. So the probability that it chooses that neighbor in a given round, and thus it pushes the rumor to that red neighbor, is at least one of the degree of the node. And there's a probability that in a given round, after this round t, no green node does that, is at most the product of these probabilities here. And then we use the standard formula here to obtain this one. And this is the quantity we lower bounded here. So this follows that this happens with some probability bounded away from 1. This means that after this round t, in each given round, with at least some constant probability, some node, some green node, will push the rumor to the red node. And so this means that with high probability, after a logarithmic number of rounds, some green node will have pushed the rumor to the red node with high probability. Yes?
Where did you use the fact that S is the dominating set?
Sorry?
Where did you use the fact that S is the dominating set?
Yes, as I said here, the probability that a node does not push the rumor to a node that belongs to the dominating set is at most 1 minus 1 of the degree of that node. If it has more than 1 red neighbors, then it's 1 minus the number of red neighbors over the degree. Okay, and okay, so this is there. I don't think it's difficult. Okay. So some applications of these results, they have been used to build faster dissemination algorithms. I will talk about this right next. Another, remember at the beginning I told you that it can be seen as a model for information spreading in social networks. So results in some way give some kind of intuition as why information spread quickly in social networks, because the result says that high expansion implies faster rumor spreading, and social networks do have good expansion. Okay, but now let's talk about this faster algorithm. The state of the art is this last algorithm. I will talk about this second paper here because it's very well very well related to what I've talked so far. So I said at the beginning that rumor spreading performs well in many graphs, but not in all graphs. In particular, not in all graphs that have small diameter. Here is an example. 2 clicks of size n over 2. The diameter is connected by this single edge. The diameter is just 3. And push-pull rumor spreading requires a linear number of steps to spread the rumor. Why? Because it takes an expectation, a linear number of steps before any of these nodes chooses the other one. Okay, so it takes a linear number of steps for the rumor to cross this edge here. So the algorithm I will talk about, there is a question of how to spread the rumor in close to diameter time on any graph. Okay, I will talk about this paper. The algorithm they propose, in fact, solves the all-to-all broadcast problem rather than the one-to-all that I talked to you, but they're not much different. So in this problem, every node has initially a message, mu, and then the goal is that each node receives all the other messages. Okay? And the main component for this algorithm is a fast algorithm for solving the local broadcast problem. In this problem, each node must learn the messages of all its neighbors nodes. Not of all other nodes. The graph just the neighbors. And it's easy to see that given a local broadcast algorithm that has running time t, we can solve all-to-all broadcast in t times diameter rounds. How? By repeating the local broadcast algorithm, by running the local broadcast algorithm for diameter many times. Okay? And so what is the intuition behind the local broadcast algorithm? So the key observation is that any graph can be partitioned into clusters of high conductance with only a few edges in between clusters. What we mean, how high is the conductance? Of order at least 1 over log n. And how few are the edges? A constant fraction. Okay? And so what the algorithm does, they run the standard push-pull for a number of rounds such that we have that with high probability, each node in each cluster, each node receives the messages of all the other nodes in the same cluster. Okay? And how long do we need to run push-pull for that? Since we have this lower bound on the conductance of each of these clusters, and since we have this bound that is on the rumor spreading time, the log n over phi, the log n over conductance, which we can apply on each of these clusters. Okay, it follows that log square n number of rounds would suffice to achieve that. Okay, from this.
Does this result have anything to do with regularity level?
No, I don't. Regularity. I don't know, but I know that the proof is not very. Okay. From what I've told you so far, you may assume that the algorithm needs to find this partition, but this is not the case. It just requires the existence of such partition, and this existence is proved. Okay, so here is how the actual algorithm runs. Each node maintains a set of the neighbors for which it has not learned their message yet. Okay, so initially SU contains all the neighbors of the node. And then it repeats the following code while as long as this set is not empty, just runs for log square n rounds the push-pull protocol, but in each time it chooses a random neighbor among all the neighbors that are left in SU. Okay, and then and then after these log square n rounds, just removes from this the set SU all the nodes, all its neighbors from which it has learned their messages. Okay, and we need something else here, some technical thing. We need to run this thing twice to make sure that if a node learns the message, if U learns the message of V, then V will also learn the message of U. But this, okay. And now we will say that we will argue that this part is executed, needs to be executed at most a logarithmic number of rounds. So the total round complexity will be at most log cube n. Okay. So this is the last slide of proof that I have in the paper. The rest is okay. Here is the simple analysis. As I said, this is just a repetition of the fact that I replied before. We have a partition of the set of vertices such that the conductance of each of these clusters is at least 1 over log n. We need to define conductance carefully here, but this is a technical, this is just a detail. And the second says that at least 1/3 of all edges have both endpoints in the same component, in the same set VI. And so using this lemma, we have that after each phase, so after this log cube, log square n rounds, each node U knows the messages of all the other nodes in the same component. Here is where we use the log n over phi bound, and this bound here. So the log square n is just the log n over this conductance here. And also at the end, we say that all these edges will be removed. All the edges inside clusters are removed, additionally more. So we're left with no more than 2/3 of the number of edges we had before. Okay? So in each of these phases, we have that the number of so this is what happens after this first phase. And then we repeat the same thing for the remaining graph. Okay? And since the number of edges drops by a constant factor in each phase, we need at most a logarithmic number of phases. So in total, we need this times this. We need log cube n rounds. Okay, so this is the intuition. And as I said, this uses this bound that we showed before. What is interesting is that a different analysis of the same algorithm, but now using this proof idea that I that I talked with the dominating state, so this proof idea, it can result in improved running time that is log square n. And essentially what it shows is that here, instead of log square n rounds per phase, we need log n. So it improves the running time by a logarithmic factor. And this is the other algorithm that I talked to you about. It has the same running time as this improved running time, but it's impressive that it's deterministic. Okay, and one very interesting open problem here is to find whether we can solve this local broadcast problem in time faster than log square n in this gossip model. So gossip model is essentially the implicit underlying model we had in all algorithms so far. So we assume that initially the graph topology is unknown, so each node knows only its set of neighbors, and each node in each round can initiate a connection to only one other node. Not necessarily a random one, but only one. Okay? And, okay. So far we have assumed that the graph does not change during the protocol. Now we will assume that it does, and we'll see how these bounds with conductance could be affected. Here is a simple model that we consider. Instead of a graph, we have a sequence of graphs on the same set of vertices. The set of edges may change. How it can change? We assume two models. Either the whole sequence of graphs is fixed in advance before the protocol starts, or it can be determined adaptively, which means that the graph for round t is fixed right after round t plus 1. So it can depend on the actual set of informed nodes at that time. Okay, so the adaptive setting is clearly more difficult. Okay? So one obvious observation is that this dynamic can delay rumor spreading. So there is some sequence of graphs such that push-pull is much lower in the sequence than in any specific graph in this sequence. Here is a simple example. We have the clicker. We start from this leaf, the first leaf. As we said before, in one round, the node in the center gets informed. The leaf pushes the rumor to that. And then what is G2? G2 just switches the node in the middle with this second leaf here. Okay? And then again the center gets informed. And then G3 switches with that node, and so on. And then we need n rounds to inform all nodes, whereas just in a single star we need 2 rounds. Okay? And moreover, note that these graphs have perfect conductance. And now, remember, I told you that our goal is to see how these bounds, say, in terms of expansion, extend to such a dynamic setting. So it's not, at the beginning at least, it was not clear how under what conditions these bounds extend. So what we observed is that the reason we have this phenomenon here is that the degree of a node may change drastically between rounds. And we also showed that if this is not the case, if the degree change only slightly, then we have a similar type of bounds in terms of some notion of cumulative conductance. Okay, so here is the bound. This is the assumption that I told you. The degree of a given node changes by at most a factor of beta throughout the protocol. This beta we assume to be constant. Okay. Note that we don't make any assumption about the degrees of different nodes. They may be very different, so the graph does not need to be regular. So if this is the case, then the running time of push-pull is with high probability at most the smallest t, such that the sum of the conductances of the first t graphs is of order C log n for some constant c. Okay. And this holds even for adaptively determined sequences. If beta is not a constant, then c is a function of beta, at most a linear one. And note that this bound implies the log n over phi bound for static graphs y, because if the graph is static, then all these are the same, are equal to the conductance of the graph. So we have t times phi here, which implies that the t is of order log n over phi at most. Okay, and okay, we have similar results in terms of vertex expansion. Now the conditions are slightly different. We require that the graphs be regular, and we require that the sequence be fixed in advance. Also here we have probably some too many logarithmic factors. About these two assumptions here, the second one is necessary, so it cannot drop completely. About the first one, the regularity of the graphs, I suspect that it's not needed, but we do need it for the proof that we have. Okay? And, okay. Last part, so I will talk about now asynchronous rumor spreading. So far we have assumed that nodes take steps in synchronized rounds, which is assumed that nodes have synchronized clocks. And in some settings, some distributed settings, this is not feasible or desirable. So for this reason, many many works have considered rumor spreading in an asynchronous time model. So what is this standard model that has been considered? Now each node has its own independent clock, which is an independent Poisson process of constant rate. This means that the time between two ticks is an independent exponentially distributed random variable with mean 1. Okay? And now it contacts a random neighbor to do what the protocol says, to push, pull, or push, pull. Each time its own clock ticks. Okay? And now this an equivalent expression for this model is that each node has an independent clock for its edge, but now an independent Poisson clock, but now the rate is 1 over degree rather than 1. And in case you're familiar with this model is very similar to the first passage percolation or Richardson model for the spread of epidemics, especially for the case where the graph is regular. When the graph is regular, I think it's exactly the same as the Richardson model. And okay, let's see how asynchrony affects rumor spreading time. Let's see these two very simple examples, the star and the path. The star, we already know the synchronous rumor spreading time is no larger than 2. But for the asynchronous rumor spreading time is log n. And why is this the case? It's because log n time units is required until all these n Poisson clocks with the rate 1 tick at least once. Okay? So in this case, synchronous is faster than asynchronous. Let's see what happens with the path. For the case of the synchronous protocol, the running time is 4 over 3 times n. Why? Because if we look at these consecutive nodes, the probability that in a round none of them chooses each other is 1/2 times 1/2 is 1/4. This implies that the expected number until the rumor moves from this to the next node is 4 over 3, 1 of this, of the probability that they contact each other. Okay? So, whereas for the asynchronous rumor spreading, the time is faster, is n, because the corresponding expected time is just 1. So you see, in this case, we have that asynchronous rumor spreading is faster than synchronous, albeit by a constant factor. So, okay, similarly to the synchronous rumor spreading, there has been a lot of works that
It's just the fact that the expectation is equal to 1. So is it wise? Is there, if you change Poisson by another distribution, but you keep the same mean, how does that affect the result?
In this example, I guess it does not. But when you have, essentially, you use, in many examples, you use the fact that the minimum of exponentials is an exponential with the sum of with the mean. Okay, let me tell you, the sum of Poisson, the minimum of Poisson, is a Poisson with the sum of the rates of all the Poisson. So this, you need this memoryless property. So many results have studied rumor spreading, asynchronous rumor spreading for specific graphs. Here is just a list. And the results that they showed, they are similar to the synchronous rumor spreading time within constant factor, typically. But there are some results also where these running times are different. Here are two results. Although they don't consider the complete covers, they consider the problem of informing 1 minus epsilon fraction of nodes. But then, for the case of this graph here, this takes only constant number of rounds in the asynchronous protocol, and like log n for the synchronous protocol, and similar gaps there are for other types of graphs. So in addition to these results for specific graphs, there are also general bounds on the relation between asynchronous and synchronous rumor spreading time that apply for any given graph. And here is a recent result. So for any graph, it holds with high probability that the asynchronous rumor spreading time is at most log n times slower than the synchronous. And the synchronous is, in any graph, at most this polynomial factor larger. So this implies that potentially the synchronous rumor spreading time is much slower than the asynchronous. Or in other words, the asynchronous is much faster than the synchronous. And in fact, they did show an example of such a graph where asynchronous rumor spreading is much faster than the synchronous. Also, they claim they conjecture that these bounds are not tight, and they gave they said which are the right bounds, and these are the bounds that we showed very recently. So we showed that in fact here we don't need this logarithmic factor here, just a logarithmic term here, and we reduce this to square root of n. The first is tight. The second, we don't know if it is tight because we don't know of a better result than this one. Okay, and the last, in my last slide, I will not talk about these results. Although this is very simple, they require some coupling arguments. But I will describe very quickly this graph here where asynchronous rumor spreading is much faster than synchronous. So here is the graph. It's a path of length n to the 1. It's a path of n to 1/3 diamonds. Each diamond has 2 nodes and n to the 2/3 disjoint paths of length to connected them. Okay, so this is the graph, and then what is the synchronous push-pull rumor spreading time? It is at least equal to the diameter of the graph. The diameter of the graph is twice this, so this. But it turns out that the asynchronous rumor spreading requires only logarithmic time to inform all nodes. I should probably not. It's a simple example. Probably I should not. I should skip it, right? Because okay. Yes. Okay. Good. I'm happy that at least one. So, yes. So, why it is so fast? First, we'll see how long it takes to go from here to there, and then we multiply by this quantity to show how it reaches there. Okay? Now, remember that the time before a given node chooses and pulls the rumor from this is an exponential random variable with mean 2. 2 because it's equally likely to choose any of these nodes. Okay? So the time until the first of these nodes pulls the rumor is the minimum of this m exponential random variables with mean 2, which is again an exponential random variable with mean 2 over m. Okay, so it takes an expectation 2 over m time before the first of these nodes gets informed, and then after square root of m times this, which is 2 over square root of m, we have square root of m informed nodes here. And then by a similar argument as before, it follows that in an additional 2 over square root of m rounds, we have that some of these nodes will choose and push the rumor to this node over there. Okay, so it takes order 1 over square root of m rounds to go from here to here. We choose m to be that. So the 1 over square root of m is 1 over n to the 1/3. And then we multiply by n to the 1/3. So we get a constant time for the rumor to go from there to there. And then we need an additional order logarithm time before every node gets the rumor with high probability. And this is, I will just conclude. So by now we have good bounds, good upper bounds in terms of expansion for rumor spreading time in graphs. We don't have essentially any lower bounds in terms of general graph parameters, so it would be nice to have some. I talked about rumor spreading in some very basic dynamic graph model. Maybe it would be interesting to study rumor spreading in more realistic dynamic models. The bound that I showed between asynchronous and synchronous rumor spreading time, the upper and lower bounds, are very far apart, although they cannot be improved if we don't consider additional parameters of the graph. But maybe it would be interesting to study more refined connection between these two quantities, taking possibly into account additional the additional information about the structure of the graph. Finally, when I talked about more sophisticated algorithms, I mentioned that it's interesting to pinpoint the exact complexity of the local broadcast problem in this gossip model, where the graph is unknown, and each node can choose just one neighbor. So in addition to that, the existing fast algorithm they tend to have not good fault tolerance property, and also they require messages of linear size. So it's interesting to see if we can address somehow these two issues. And thank you very much.